This is the third video in a series prepared by the Permafrost Technology Foundation to help the housing industry in Alaska cope with permafrost. The first video dealt with the concept of permafrost, acceptable types of foundations on permafrost, and how to determine if an existing house is on permafrost. The second video dealt exclusively with the permafrost investigation, how it is performed, and how to interpret the data recovered. This video covers the options that one has if they own a house that has undergone settlement due to thawing permafrost. I'm Dr. Tom Kinney. I'm the Vice President of the Permafrost Technology Foundation. I'm also an Associate Professor at the University of Alaska Fairbanks, and I'm a Vice President of Shannon & Wilson Incorporated, a geotechnical consulting company that deals with structures on permafrost. If your dream home used to look like this, and now it looks like this, you probably didn't view the first video before buying and probably didn't do a permafrost investigation. You probably have ice lenses, ice wedges, or other ice masses under your house. The road in front of your house probably looks like this, and you probably have thermal karsts that look like this in your yard. You have to make a decision. You could abandon ship and lose your entire investment, or you could fix it up, which will probably cost tens of thousands of dollars. To salvage a foundation system that's been damaged due to thawing permafrost, we have to lift and re-level the structure. We have to install a new foundation system. And then we have to repair the damage that was done during the settlement and the re-leveling. Now, to stabilize the foundation, we can either stabilize the site, we can support the structure below the ice-rich permafrost, or we can install some kind of a re-leveling system. Now, re-leveling systems have a number of advantages. They're independent of the soil properties, they're independent of the heat load, and they're absolutely fail-safe. They'll always work. But they do require continued maintenance. The post and pad foundation consists of several pads placed on the ground with posts between the pads and the bottom of the house. The pads are generally placed on gravel, which is placed on the original ground. The floor is usually elevated to allow a free flow of air under the house to slow down or stop the thawing. Under the right circumstances of weather and surrounding terrain, thawing will be stopped and re-leveling will not be necessary. However, it is likely that this will not be the case throughout the life of the structure, and re-leveling will be necessary. Re-leveling by installing new posts is relatively easy, but frequently jacking systems are built directly into the support members. One key and often overlooked feature of a post and pad foundation is the need for lateral restraint to resist earthquake and wind loading. Grouting may be the re-leveling technique of choice under structures with a slab-on-grade foundation. It takes a skilled crew to use grout jacking to get a uniform product in the end. If this technique is used, it causes minimal disturbance to the house and yard. However, it doesn't address the primary cause of the settlement, and it is likely that future re-leveling will be necessary. Each time a cement grout is used, it becomes progressively more difficult to re-level the next time. Hence, it should only be used in cases where repeated re-leveling will not be necessary. Foam and other plastic grouts avoid some of this problem and add insulation to the areas which have settled the most. Installing a stiff foundation will eliminate the local settlement. However, it takes a very stiff foundation, and it will not keep the house from tipping on a plane. A stiff foundation in itself does not address the cause of settlement unless it's combined with other techniques, such as cooling of the ground. The triadetic foundation was developed in Canada in the late 1980s and has been marketed throughout the North American Arctic. It is a form of a stiff foundation which has several advantages. It is composed of lightweight sections that can be transported and assembled easily, and it raises the structure to allow cold air to flow underneath. The feet are intentionally small so that they will sink into the ground in the high spots. The foundation system can be purchased with re-leveling screws built directly into the feet. Without this feature, this foundation is difficult to re-level because the entire underside is covered with a matrix of pipes. This may be the best type of foundation for earthquake resistance because it allows the structure to move horizontally on the ground surface without transmitting lateral forces to the structure. Pile foundations are interesting. Piles are installed deep enough to avoid future settlement, hence releveling should not be necessary. Deep enough means either through the ice-rich permafrost or far enough into it so that it can develop support below the maximum depth of thaw. If the house is elevated on piles, it helps to reduce future thawing. It is generally easy to relevel a pile foundation if necessary. Pile foundations generally provide good lateral resistance. Piles come in many different forms, including steel, timber, or the A.B. Chance helical pier system. They are usually installed in a hole drilled in the ground, and the annulus is filled with slurry. However, they may be driven under some circumstances, or they may be driven into a pre-drilled hole. The A.B. Chance system is screwed into the ground. Some piles have fins or helixes below grade, which help provide support, and some have thermal probes associated with them for extra cooling. Now let's look at several ways to stabilize the site. As we have discussed before, one way to reduce the amount of thawing is to elevate the structure. This does several things. It stops the heat from the house from going directly into the ground. It lets cold winter air get under the structure to refreeze the area. It keeps the insulating blanket of snow from covering the ground under the house in the wintertime, and it keeps the summer sun off the ground in the summer. It is usually desirable to build a deck on the south and west sides of the house to expand these benefits outside the perimeter of the house. Additional benefit can be gained by providing external shade, particularly on the south and west sides. Shade can be provided by large vegetation, fences, unheated structures, or topographic relief. The goal is to get the average annual surface temperature to be below the freezing temperature of water within the zone of influence of the house. If this can be attained through the above means, then thawing will be stopped and the ground will be stabilized. Unfortunately, it may take several years for stability to be reached because of the heat that's stored in the ground. If this cannot be attained because there are other heat sources such as groundwater flow, then more drastic measures must be taken. The next option is to close in the crawl space and install a forced ventilation system. Fans are installed on one side of the house and vents are installed on the other. Usually the fans are on the south side and are directed to pull air out of the crawl space. The fans are turned on anytime the crawl space air is warmer than the outside air. It is easy to wire a thermostat so that this can be done automatically. This system will get the average ground temperature cooler than the elevated house if it's properly maintained. If the ground cannot be cooled enough with free or forced ventilation, then it will be necessary to install some form of refrigeration system. The mechanical refrigeration system is like a big freezer in the house that circulates cold fluid under the insulated floor. This system can be controlled very accurately if properly designed and installed. However, it must be monitored and maintained, and there are operational costs. The operation may be somewhat tricky. The ground surface under the cooling system must be kept at the right temperature. If the ground gets too warm, the permafrost will thaw. If the ground gets too cold, frost heaving may occur. Frost heaving is particularly dangerous in this environment because the temperature is kept cold for long periods of time. In nature, there is a limit to the amount of frost heave that can occur because winter eventually ends. Under a refrigeration system, winter never ends. Thermal siphons are pipes that are placed part above ground and part below ground. They extract heat out of the ground in the winter because the top of the pile is colder than the bottom, and they do nothing in the summer because the reverse is true. The theory is that more ground is frozen back in the winter than is thawed in the summer. There are two basic kinds, the single-phase and the two-phase. The single-phase system is filled with fluid. When the fluid at the top is cooled, it gets heavier and sinks to the bottom. The lighter, warmer fluid at the bottom circulates upward, carrying heat with it. There are several levels of sophistication of single-phase systems. They may consist of a single pipe with or without a baffle or inner pipe to aid circulation. They may also consist of a loop so that the fluid flows in one direction all the time it is flowing. The two-phase system is part liquid and part gas. The two are in equilibrium at the temperature of the gas-liquid interface. When the top gets cold, it condenses some of the liquid on the inner walls of the pipe where it runs down the inside of the pipe. This condensation takes molecules out of the gas, which reduces the gas pressure. The lower pressure at the gas-liquid interface causes the fluid to boil, which cools the fluid. There are advantages and disadvantages to each system. However, both do about the same thing. The advantages of using the thermal siphon is that they have no moving parts and should work forever without needing external energy. Forever is a long time, and they have been known to develop leaks or be damaged in other ways and stop working. Installing thermal siphons under an existing building is a real challenge. There are several techniques, however none of them are foolproof, and proper installation is as important as proper design. Unlike the mechanical refrigeration systems, frost heave does not seem to be a problem, probably because of the radial freezing and the deeper depths of the installations. Now that we've had a chance to take a look at the range of options, let's go out in the field and take a look at some actual installations. I would like to introduce Dave Thompson of DCT House Moving and Releveling in Fairbanks. They have been in the business of releveling, moving, and installing foundations under houses since 1985. They've worked on well over 200 houses in interior Alaska and many in other remote locations. Dave and I will trade off showing different installations.
The house originally sat on the concrete stub wall behind us and these pads supporting the floor section. There were several of these pads. It was very hard to relevel the house at that time. By supporting the house on a steel beam instead, it has cut the work for releveling the house down enormously because we have 6 points now that we have to look at to relevel this area instead of 50 points. This is what we use to check the houses for level. It's fast. There are several ways we use water levels also. The rotary laser is the fastest and easiest in a crawl space like this, where you have a nice wide open room and it's easy to see what's going on. It'll draw us a level beam all the way around here when we start to rotate it, or we can pinpoint it like so at each one of the jack points. This is the original concrete stub wall and footing right here. When we come on in, we blast a hole through this concrete stub wall and we insert the beams underneath the house. Then we lift and raise the house up to level on the steel beams. Then we install the saddle. In the saddle system here, we drop a piece of rebar down the concrete columns on the block with a rebar in it and attach it to the saddle, pour it full of cement. The beam then sits directly into the saddle. The weight of the house is on the beam. In the saddle, nothing is sitting on the concrete stub walls except for where the saddle is attached. All right, with the laser we get our reference point as to how far out of whack the beam is. This one's at 13 5/8. If we wanted to go to 14 to get to where we need to go, then it's set up so that a person can come grab a hold of it and start cranking it up. You can go on each one of the bolts. You can see it's raising there about 1/4 inch. And then this one's loosened up. You rotate this side of the beam up. You can hear the house starting to raise right there as it comes up. There, we've lifted the house about 1/4 inch on that one.
This house was originally constructed on a fairly conventional foundation in the hole that's right behind me. It settled about 3 feet. They moved the house over to the new location. They built a very stout foundation wall. It's about 3 feet deep and 8 inches wide, and it's a reinforced concrete wall that's very stiff with a footing underneath it. And then the house settled another 2 feet after that. And we went underneath the house, lifted it using pneumatic jacks, then set the house back down on pea gravel. And then we turned the crawl space, which was a heated crawl space then, into a forced ventilated system. Here's the intake fans with the louvers set up so that the snow doesn't block the intake. And then we have fans on the other side, and we have a computer-controlled system inside that draws cold air through whenever the outside air is colder than the crawl space air.
On this house, we had an ice lens directly in front of the house that was melting and causing the dirt up here to slump off down into the void left by the ice lens. So we picked this house up, moved it back about 12 feet, and this is the releveling system we put back underneath it. It's a 9-inch thick concrete footing, or concrete pad, with tied rebar mat in it. We've got a plate mounted in here to keep a bolt coming out of here, very stiff, rigid, inside of a pipe, where this is a nice, easy to re-level system also. If this starts to settle, we can take and crank this one up, and we've got about 1.5 feet of adjustment on it. With the beams here, they also extend out the back, and we have the decks in the porch hung off from the steel beams, which means we don't hit any of the frost heaving or jacking, seasonal frost jacking that comes along with a lot of the lighter decks and porches. It also helps create the shade for the pads to keep them from thawing and going down anymore.
This house is resting on about 40 feet of a very high water content silt, and under that is solid ice. We put the thermal probes underneath the house to freeze the area back again. The thermal probes were installed using directional drilling, and it's a technique that's used extensively for putting electrical wires under roads and things like that. And the contractor came over here, put down a pit in here that was about 5 feet deep. Then we drilled the pipes under the house and then up on the other side of the road. And then we grabbed a hold of a pipe on the other side of the road and drug it back underneath the house. Then we came over here, dug another pit where the thermal probe will go, cut the pipe off, and put the thermal probe section on top of it. Typically we need probes on about 6 to 10 foot spacings underneath the house.
This house, when we moved it in, it was during the winter. So the gravel pad was built in wintertime with frozen material, and it's on very poor soils. High moisture content and silt. The ice is at 10 to 15 feet, so we know we're going to have a lot of settling and some maintenance on this house. So the system that was designed and put under here was an easy to re-level screw jack system. It's got a base, steel base on it with the bolt dropping down through the pipe here, the nut and a couple thrust washers. This can be turned up for re-leveling by putting a pipe wrench on the nut and cranking it up. You've got just about 1.5 feet of adjustment on this system right here. So as it settles, you can take, if you're running out of adjustment, you can block up in front or behind this, go ahead and pull this jack out. It weighs about 140 to 150 pounds. Put some fill back underneath it and reset the jack and be good to go for another couple years. This system makes it ideal for this kind of a ground where you know you're going to have to do maintenance every year on this house.
This house was originally on short wood piles. The piles went through the active layer down about 3 feet to the top of the ice-rich permafrost. As the site warmed up, the thawed layer became deeper, and then the piles started to settle. So we lifted the house and put it on a triadetic foundation. The triadetic foundation consists of a whole bunch of small parts that can in fact be flown in an airplane very easily. It's very easy to construct one. 2 people can put one together in an afternoon for new construction. It's much more difficult to put one under old construction. We had to lift this house, build a foundation under the house, and then set the house back down. That took 4 people about 3 days to do it.
This structure, when we arrived, was on a shallow pile foundation. The soils underneath it are very poor. They're highly saturated silt to 15 feet with ice starting at 20 feet. The structure was settling, causing damage to the skirting on it. The owner mentioned he wanted a garage. Our solution to this one was to build the gravel pad with a concrete footing, very heavy concrete footing right here underneath it, raise the house, put the garage underneath. The concrete footing is built so that it will maintain and act as a beam, making the house very easily re-leveled by digging underneath it, placing airbags, and re-leveling it. This is the hydraulic power pack we use for controlling our hydraulic jacks when lifting the house. With this manifold system and the valves up front here, I can control either a corner jack or I can take one end up at a time. We have very good control of however we want the house to go up, whether it be uniformly or a fine adjustment of one corner at a time.
This house had an enclosed warm crawl space. There's about 30 feet of wet silt underlined by ice-rich permafrost. It was in the process of settling about an inch or so per year. It had settled about 30 inches when we got the house. We removed the walls from the crawl space and opened it up, and then we placed the whole structure on these crib foundations, and then left a space in the middle of the crib here where we can put jacks in very easily and re-level the house anytime we want. Now these cribs have to be tied together, and they have to have certain dimensions to keep the house from tipping over in an earthquake. Another feature of this, we put a deck out on the south side, and then we have a sheet metal bottom to the deck which directs the water then out away from the house and out to the yard. Another feature installed in this house is a geosynthetic wall to replace the old wood stem wall that was in the around the outside of the structure. And to do this, we put in fabric. This is a plastic material basically called a geosynthetic. And we would have a 2x12 that would be up standing vertical. The fabric would come out up over the 2x12. Then we would fill dirt in behind, lay the layer of fabric over on top of the dirt, and then go up with the next layer. We've got 1, 2, 3, 4 layers of geosynthetic in this particular installation. These lifts are typically 10 to 12 inches high. It's a very cheap wall to construct. It's easy to do for an individual as far as that's concerned. This facing material should be covered with something to protect it from the ultraviolet light. This structure has a daylight basement. The floor slab is about 4 feet below the outside grade, and the structure had settled about a foot. It's on about 30 feet of very wet silt underlined by ice-rich permafrost, and it was continuing to settle. We re-leveled the structure by pulling up the floor and going underneath the footing with pneumatic jacks and then lifting the whole footing and everything up. Then we backfilled underneath the footings, and then we are stabilizing the ground using a heat pump. Now to do that, we put down 4 inches of sand, and then we put plastic pipe that goes back and forth on top of the sand on about a 9-inch grid. Then we have 4 inches of insulation on top of the plastic pipe, and then this plywood that you see on the floor sits on top of the insulation. This is the heat pump. This heat pump basically circulates cold fluid through those pipes underneath the floor. So it's taking the heat from the house that would go down and melt the permafrost. It goes down, gets picked up by those pipes, and gets brought back to this unit. Then in the wintertime, when we need heat in the house, this unit then vents the heat into the house, and it's part of the heating system for the house. In the summertime, when we don't need heat in the house, then the heat is vented to the outside. The heat extraction is very efficient. It takes very little electricity to move the heat from underneath the floor slab up into the house. Unfortunately, we only want that heat in the house about half the time. So half the time we're running the unit and then just venting the heat to the outside. Now this whole thing runs on a series of zones, and the zones are controlled inside this box. And now we'll come over and take a look inside the box. This pump circulates fluid throughout the entire system. There are 5 zones for different parts of the house. One of them circulates around the outside of the house. The other 4 are for different areas in the house. We have to adjust each one of these zones so that we get the same amount of coolness, if you will, throughout the entire system. And then the pump is turned off and on based on the temperature of the ground below the structure. If the ground gets too warm, then we turn on the pump and we cool down the system so that we avoid thawing permafrost. On the other hand, if the system gets too cold, we'll get frost heave. So in fact, if we get very far below 32 degrees, Then we turn the system off so that we don't supercool the system and get frost heave under the structure. This house is constructed on a thickened slab foundation. The house is small enough that we could put bag jacks under the edges and lift the foundation, floor slab, and house all at once. Usually 12 to 16 bag jacks are used. They're controlled by a distribution manifold, as seen here, operated by Glenn Pearson. Each jack is attached to a valve and can be controlled independently. Water levels are used to control the lifting of the house. One end is placed above each jack point, and the other is placed on a table in the same relative location as the jacks under the house. A marker is attached to each tube at the initial location, and another one is attached at the desired final location to monitor the progress during lifting. Travel was forced under the house using an air siphon mechanism developed by Glenn Pearson. Now that we've seen the options, I'll present some rough costs. To a large extent, these costs are going to be determined by what kind of a foundation your structure has now, how much distress the structure has undergone in the past, what kind of a foundation system you want, and whether or not the house was allowed to freeze. Now, all costs are going to be based on 1998 technology and prices, and a house footprint of about 30 feet by 40 feet. Let's look at releveling first. There are 4 basic kinds of support. The easiest foundation system to deal with is the post and pad or pile foundation. If there are relatively few support points, the posts or piles may be replaced with jacks. If there are many points, it may be necessary to support the house on a few big beams and then put jacks under those. This kind of releveling can usually be done for under $5,000 plus materials if we have to buy beams. The spread footing with structural floor system presents another problem. Individual support points are much like the post and pad foundation and can be replaced with individual jacks, or those points can be supported on beams, which in turn are supported on jacks. The strip footings are more difficult. It may be possible to break the foundation loose from the house and lift the house alone. And it may be possible to put jacks under the footings and lift the foundation, stem wall, and house all at once. Which approach is best depends upon many factors, including the condition of the existing stem walls, the depth of the foundations, and the replacement foundation type. Lifting and releveling houses on this type of foundation usually cost between $10,000 and $15,000. A slab-on-grade foundation is the third type. In general, the house is supported on spread footings with concrete or masonry block stem walls up to at least the first floor level. The floor is concrete, poured directly on the prepared ground surface. Usually, the floor is poured up to the edges of the stem walls and is separate from the rest of the foundation. However, there are instances where the wall is tied to at least the perimeter foundations, either through steel reinforcement or structural concrete joints. Lifting and releveling the spread footings and stem walls is not significantly different from the previous systems discussed. The problem comes in what to do with the concrete floor. Concrete floors are expensive, and there is a tendency to try to save them. Careful thought should be given to this decision. Generally, it is better to abandon the concrete floor and replace it with a wood floor, which is structurally supported on the foundations. Sometimes it's better to remove the concrete floor and raise the house from under the footings, as shown on side A. And sometimes it's better to cut the house loose from the stem walls and lift it on the stem walls, as shown in side B. Lifting and releveling this type of foundation usually costs between $10,000 and $20,000. The last type of foundation is commonly referred to as a thickened slab. The footings are poured monolithically, with the floor as a single unit. If the foundation was properly designed and constructed, it is usually possible to lift the entire footing, floor, and house at the same time. There may be some sagging, which may cause some distress to the house that was not already there, but it's nothing that isn't repairable. The entire house can be lifted far enough to support it above grade, or the space may be grouted. Lifting and releveling houses on this type of foundation generally costs between $10,000 and $15,000. Now to summarize the cost of lifting and releveling the house. Releveling a house on a post and pad or a pile foundation usually costs less than $5,000. Releveling a house on spread footings with a crawl space usually costs between $10,000 and $15,000. Releveling a foundation with a slab on grade usually costs between $10,000 and $20,000. And releveling a thickened slab usually costs between $10,000 and $15,000. Now that we have the house lifted and releveled, how much will it cost to put a new foundation system under it? The best type of foundation system will depend upon a number of factors, including the present foundation system. For instance, if you're already on a post and pad system, you're probably best off staying with that. If you have a slab on grade basement, you may well want to use a refrigerated system. Acceptability of future maintenance. Some homeowners think nothing of monitoring and releveling their houses, and a permanently installed screw jack system works very well. It is part of normal maintenance, much like trimming your hedges if you live in Southern California. Others, and most banks, want a stabilized foundation system, requiring you to either use piles or to stop the permafrost from thawing. Functionality. Houses can function very well when elevated a few feet. Garages do not function very well under those conditions. You need to set the ground rules for your finished product. Aesthetics. This is a very personal issue. Do you want your house up in the air or not? Do you want thermal probes in your backyard or not? Budget. I am sure we all want a top-of-the-line fix, but the reality of the situation is that budget is a big consideration. It is difficult to justify spending $40,000 to fix up a house that would originally cost $150,000, but will be worth less than $50,000 after it's fixed. How much will a new foundation cost? There are a lot of variables, but in general you can expect to spend about $5,000 to $10,000 for a post and pad foundation, $15,000 to $20,000 for a tridetic foundation, $30,000 to $50,000 for thermal probes, $20,000 to $40,000 for piles, $20,000 to $30,000 for mechanical refrigeration, $5,000 to $10,000 for forced ventilation, $15,000 to $25,000 for a stiff foundation, and $10,000 to $20,000 for grouting. Now that we have the house on a new foundation, let's look at the plumbing. Many houses that have experienced permafrost damage have been abandoned for some time. If the house has not been allowed to freeze, then there is a good chance the interior plumbing made it through the settlement and subsequent moves without breaking anything. If it has frozen, there is a good chance that there are many breaks requiring perhaps as much as $10,000 in repairs. The only thing left to do is to repair the damage that was caused by the settlement and the releveling. There are two types of damage, structural and cosmetic. Let's take a look at the cosmetic first. Cosmetic damage includes things like cracked wall coverings, cabinets pulled away from the walls, doors and windows that don't fit right anymore, and separations in molding. If there was any masonry in the house, like fireplaces and bathroom tiles, this was probably destroyed. These items may cost many thousands of dollars to repair, but the repair is completely optional. The more insidious damage is structural. The house may look like it's returned to its original position, but every time you work a joint, it loosens and it loses some of its strength. In addition, roof trusses and floor trusses may break. In general, you can't see any of these problems unless you look closely and know what you're looking for. To make matters worse, you won't know about a broken roof truss until the next heavy snowfall, or a broken floor truss until you have lots of company over on Saturday night. Either may show up during an earthquake or even high winds. A permafrost-damaged house must be inspected by a qualified engineer and appropriate structural repairs made. These repairs may reach many thousands of dollars. To summarize the cost of repairs, if the house is not frozen, you may not have to spend anything for plumbing. If the house has frozen, you could easily be spending up to $10,000 for plumbing repairs. If the house is settled less than 6 inches, structural and cosmetic repairs will be minimal, and you'll probably spend less than $5,000. If you've had 6 to 18 inches of settlement, you will have to do some structural and cosmetic repairs, could be up to $10,000. If you've experienced 18 to 36 inches of settlement, you could easily be spending up to $20,000 for structural and cosmetic repairs. In summary, if you have a house which was damaged by permafrost and you want to fix it up, it must be lifted and re-leveled. It must have a new foundation installed under it. You must evaluate and repair the plumbing. You must do any structural repairs that are necessary, and you'll undoubtedly want to do some cosmetic repairs. Do not start this without doing a careful economic analysis of the costs versus the benefits.